Hi students, welcome. We are back with chapter 3, part 2, properties of convolution and the interconnection of linear time invariant LTI systems. So there are three properties of convolution, which is commutative, distributive, and associative. For the commutative, you have xn times to hn equals to hn times xn yields yn. If drawn into a block diagram, so you have xn as the input signal going into the system of hn, and will give the output of yn. Similarly, for if we interchange the two sequence, so you have xn as hn as the input to system xn, and the output is yn. Cascaded commutative is when you have several systems, and then you can interchange the location of the systems, and it will still yield the same result, the same output. For distributive, okay, a distributive property helps you to break a complicated convolution into simpler ones. So if you have two systems, you can break it into two systems, okay, or you can combine it as one. And so, the combination can be in the form of addition, right? So xn times h1n plus h2n is similar to xn times h1n plus xn times h2n. Will give you the same result as yn. Associative is a property that is similar to the cascaded commutative. So you can see here the order of two systems can be interchanged without altering the overall input-output relationship. So you have here xn times h1n plus h2n equals to xn times h1n plus xn times h2n, right? So in the first diagram, you see that this is the associative property, and the second diagram is shown as associative and commutative property. So you can see that this is interchangeable, okay, and this is on the associative is a addition or summation of two systems. Right. Now we look into the classification of linear time invariant system. So there are 5 classifications, which are linearity, time invariant, causality, stability, and memory. So linearity and time invariant are to ensure that the consistency of the output of a system, and causality and stability are to ensure the practicality of implementing the system. So to prove that a system is linear, okay, a linear system obeys the superposition principle, where yan, okay, equals to two different inputs, summation of two different inputs, okay, goes times to the system t, will gives you yan. All right, ybn, okay, is written as one input x1n times to the same to tn, okay, and plus t x2n. So here you see that x1n times to one system and goes into the summing junction, and x2n, a different signal, goes into the same system, okay, but is written is drawn separately, goes into a summing junction, and give you ybn. So yan, if it equals to ybn, then this system is linear. So let's look at an example. Okay, if you are given a system yn equals to xn to the power of 2, right? Now you have to write that xn is two different inputs, okay? It's a summation of two different inputs, x1n plus x1n and x2n. So in other words, you can write it as xn equals to x1n plus x2n. Okay, and we write the system. So here xn replaced by this definition. So you have x1n plus x2n to the power of 2. All right, and then you expand the equation and you get this. Right, now we have to do the second condition, right, of ybn. So in this case, what you have to do is, since if you look into this in the previous slide, so you see that the x1n times to the system, x2n goes into the same system. So the best way is that you can write it as such. Okay, so y b1n equals to x1n to the power of 2. Then you have y b2n equals to x2n to the power of 2. And then you have y bn equals to y b1n plus y b2n. So you have y b1n, y b2n. So compare these two equations. When you comparing yan and ybn, it is not the same. Therefore, the system is not linear. Okay, right. Another example. Again, you are given a system and you are asked to determine the linearity of the system. To determine the linearity of the system, again, you have to let xn equals to xn and x2n. So xn equals to x1n plus x2n, right? And then you rewrite the system. So for xn, okay, replace with x1n and x2n. For xn minus 1, okay, so here you replace xn, okay, so x1n as x1n minus 1, x2n as x2n minus 1 times 2. Okay, so you have two inputs here. So this, you replace this part. Okay, right, and then again you expand the equation. Right, so once you expand, leave it there, and then you do the second part, ybn. So ybn again is similar, so you do yb1n equals to x1n plus 2x1n minus 1, yb2 equals to x2n plus 2x2n minus 1. Okay, and then you combine the two, ybn equals to yb1n plus yb2n. Okay, so you have here yb1n and yb2n. Then you compare the two equations and you see that it is similar. So if it's the same, then this system is linear. Okay, right. Next to the next property, we go on to the next property, which is time invariant. Time invariant is when the output of the system is similar when a specific delay is applied to either input or output of the system. So means that if a delay is applied to the input xn, so D is delay, capital D is delay here, and you apply also a delay at the output. So yn becomes ynd. Okay, so when you apply the delays at either end, at both ends, you will get the same equation. Therefore, the system is time invariant, right? So it doesn't change according to time explicitly. Okay, so don't make the mistake. Dia tak change according to time. It change according to time because as you know that xn, this n, yn in brackets, this is changes in time. But what we are talking about is that when you have the n outside of this bracket. Okay, let's see some example. Okay, for this system, determine the time invariance of the system. So you are given a system, all right? And then the first thing that you have to do is you delay the input. Okay, so when you delay the input, xn becomes xn minus nd. Xn becomes xn minus nd. So here, okay, xn becomes xn minus nd. All the xn in the system must be changed into xn minus nd. So you have xn, xn minus nd. You have xn minus 1, so you have xn minus nd. Minus 1 minus nd. Then, okay, this is the first step. Then you have to delay the output. So when you delay the output, that means you have to delay all the n's. So the n's become n minus nd. N minus nd. All right. So all the n's that you see inside here becomes minus nd. All right. So simply add inside the brackets n minus nd, here minus nd. All right. So when we compare the results, okay, compare between the two, when the results when delayed at the inputs is the similar or same to the delayed of the outputs, then time is yn is time invariant. Okay, remember, again, to test, to carry out or implement the minus delay input, minus whatever inside the input signal bracket with nd, means that you change xn to xnd to test whether to do this test or to delay the output, change all n's into n minus nd. Okay, that's how you do it, right? Then when you compare the two equations, if it's the same, then yn or the system is time invariant. Let's look at another example. So you have here another system, yn equals to x2n. So again, the first thing that you have to do is delay the input and rewrite the system. So when you delay the input, xn becomes xn minus nd. All right. So xn becomes x2n minus nd. Okay. Now, when delaying the output, you must change all the n's, okay, into nd. Okay, nd. Right. So here, what happens in this sorry, n minus nd. Okay. So in this case, whatever n that you find, okay, in this case, x to n, only the n, you focus only on the n. The n becomes n minus nd. So in this part, n minus nd, okay? And when you expand or you rewrite this, it becomes x to n minus 2nd, okay? So this is the output. So the output, yeah, when you delay output. Okay, so let me clarify that again. So when you delay the output, n becomes n minus nd. So n, just n, okay, not xn, yeah, n. So n becomes nd. N becomes n minus nd. So you write here as n minus nd, then you expand, you have your output here. So when you compare these two, you see that the system is not the same, and so it is not time invariant. Okay. Similarly, if you are given, okay, another example, okay, another example. So yn equals to, let's say, 2nx. Okay, so when you delay the, for the first step, we need to check whether the system is time invariant or not. So we delay the input. Okay, when you delay the input, you write as t x, okay, xn minus nd. So this is equals to 2xn minus nd. Okay, remember just this, xn minus nd. Then you delay the output, delay the output. So you write as yn minus nd. So all the n's must be minus nd. So in this case, this is 2n minus nd, xn minus nd. Okay, so what you have here is 2n minus 2nd x and d. Okay, so when you compare the two, the equation from the delay of input and the equation of delay output, you have something that is also not similar. So this system is not time invariant, or rather we call it as time variant. So it changes due to the variable of the n. Okay, now the next property is causality. Causality means that the system only involves current and past input values. Okay, so when past values are at time n minus k and at n. Okay, so this is causal. This is causal. Future values, if a system has future values, then it is not causal. So causality is important when dealing with online system, because the system does not know what the future value is. Thus, it is impossible to compute the unknown value. Okay. However, non-causal system is not a problem to an offline system, because the input value has been stored earlier. Right? That is. So let's look at some examples. Okay. This particular system, this is present at n0, n1, and n2. Okay, so this system is causal because no future values are involved. Right, now the second example, alpha n minus 1 un, time is only represented by the square bracket, so we are referring only to this part. Thus, only current values are involved. So this system is causal. Now, the third system is xn minus k. K is between -2 to 1. So when you expand this equation, you see that you get xn plus 2, xn plus 1, xn minus 1. We know that this 2 is on the left-hand side of the axis, and so that is future values, and this is what we called as future values, so that the system is not causal. All right, the system is not causal. Right. Now, stability. A system is said to be stable if a bounded input to the system produced a bounded output. Okay, so BIBO. BIBO system is bounded input, bounded output. Right. So the yn and xn is smaller than infinity, where xn and yn does not have a value of infinity at all values of n. Stability is important for practicality because no computer or any digital processor can compute using the infinity value. When computation cannot be done, the system will hang or crash. So it is important to keep the system stable by avoiding the infinity value. So example, so you are given a system here. Output yn only depends on three values of xn at different n. Now, if xn is bounded, output will also be bounded, so the system is stable. So if xn, okay, if is xn is delta n, for instance. So delta n is just at the at 1 point, yeah. So if xn is delta n, then it is a system that is an input that is bounded, and it will produce a bounded output. Now, for this system, bounded input does not ensure bounded output. For instance, if xn is un, okay, it's a unit step, and when n is infinity, then y infinity will not have infinity value, where y infinity equals to 1 plus 1 plus 1 until infinity, so the system is not stable. So in this case, you have to definitely, for all systems, you have to see what is the input. All right, so if you use delta n, it's fine. If you use a rectangular input, is also fine. If you're using a finite length input, is also fine. But if you're using anything like ramp equation or step function, ramp function or step function, then your system will be unstable. All right, now memory. Okay, memory is a system is said to have a memory if it consists of non-current inputs. So a system that consists only current inputs is memoryless. Okay, so means that a system that has past or future inputs, then it is a system with memory. A system that is only has current input, then sorry, I have this on backwards. So if a system that has past and future inputs, then it is a memory system. So current a system that has current input only, this is a memoryless system. So for a real-time system, it has to be causal and with memory, okay? Because if it has to work with future inputs, so you have to add in prior data so that it can continue to process. All right, so that is a function of memory. Okay, now here are some exercises systems that you can try. So you can see you can check the linearity, causality, stability, and time variance of the system. And okay, you can also check whether these signals here, input signals, are bounded or not. All right, so try this exercise and compare your answers with each other, and I will provide some of the answers later on. Okay, now as a conclusion, okay, so this is your assignment. Your assignment is actually mapped to PLO teamwork. Okay, so what you have to do is make a video of two types of LTI system classification. This is linearity, time invariant, causality, memory, and stability. choose two of them, but one must be linearity or time invariant. So it's either you can choose linearity or memory, or you can choose time variant with causality, or time variant with stability. So that is the pairing. Okay. So make a video about two types of LTI system classification. Then for each classification, show one example. You can use the examples from the previous exercises. Okay, proof the system is according to the classification that you have chosen. Then for each of that classification, include a real world example. Okay, a real world example. And the video should not exceed 20 minutes. Okay, since this is a video, okay, I would recommend that you work and make this video interesting. Not necessarily that you have to use Powtoons or with animation and such. If your explanation is interesting, the way that you give your examples, this is also acceptable. Okay, what is important is the message of your assignment or your content is delivered clearly. All right, I don't want any mishy-mashy, all this glitter and all decorations and all this animation, but your content is lost. What is most important is the content is clear and the content is delivered in a precise and clear manner for the viewers understanding. Okay, so the assigned date is today, 24th of November, and the due date for your assignment to be handed in is on the 7th of December, 12 midnight. All right, I will instruct your class rep on how to submit your assignment. Okay, so no worries about that. Now, your assignment will be assessed according to the following attributes given by MQA. All right. So verbal communication is very important. Is the delivery of your video very clear? The way you say the way you speak in your video, the way the content is delivered. Okay, is it clear? Is it effective? Is it confident? And so this clear, confident, effective. Okay, all right. And then obviously there's no audience during this, so this is not included in the assessment. Now, written communication. So any written part in your presentation will be evaluated uh, based on this. Okay, is clearly written, is coherent, means that the flow of your presentation is logical, it makes sense to the audience, and it's systematic. All right, and then okay, you are also evaluated upon leadership attributes. That means that you as one of the team members will be assigned as a leader. All right, and basically not really as uh, how do you say, an extra mark. Is rather that I will combine these two together so that I can see whether you are fulfilling your task as an active member in the group. So how I will apa ni, assess this is through your contribution. Okay, the contribution of each member toward the video. So I need that in the introduction of your video that you outline what are the roles of each member, or maybe not in the video, you can write it as in a description of your videos. Okay, so means that you hand in your video and then there's a your names, send also a note of the name, your names and your matrix number and description of your task, the task of each member. Okay, so Let's say if one video is really, really good, but I find that certain parts are missing, or one part of the video is a bit lacking, then I will look into the task or the roles that have been assigned to each member, and I have to see who is responsible for that particular section. Okay, even if a video is really bad, okay, but one part is really, really good and is outstanding, then I will have to give a different mark for that particular section. All right, so if you have any questions, or you are not certain about certain parts, um, you're not certain about any parts of the lecture, please contact your class rep, or you can also contact me directly. All right. So thank you very much. Wait for the next lecture.